In this video, we will calculate again the electric potential, and this time we will find the potential using the ring charge particle, which means that we will calculate and we will derive a relations of the electric potential of a ring charge from the center of the ring. If you remember in our previous videos on ring charge, we solve the electric field at a distance x from the center of the ring. Now today, let us use again this ring, but this time we will calculate how much is the electric potential. Now let us recall first, if we are given a point charge whose charge is a positive q, then you are asked how much is the electric potential at a distance r from the center. Then in our previous video, we are able to answer this question because this is a point charge. So therefore, to calculate the electric potential of a point charge at a distance r from the center is just simply multiplying the constant, electric constant, which is the 1 over 4 pi permittivity, the source charge or the stationary charge divided by the distance from the center of that charge. So therefore, substituting all values here, and we are able to calculate the electric potential of point charge. Okay? So the question is this applicable to a ring charge? Meaning, if we are asked how much is the electric potential at point P from from point from the center of the circle towards that point, is it the same? 1 over 4 pi permittivity Q over R? The answer is no. Why? Because this 1 over 4 pi permittivity Q over R is intended for point charge only. So therefore, what will you do in order to solve for this electric potential of a ring charge from the center of the circle? Now, the strategy is to consider a segment of the ring. Call this as dq. Then after that, we will consider this now as a point charge. Okay, so therefore, if we cannot use this one, then let us divide this ring into its segment. A very, very small charge, call it as dq. And that dq has a distance r from that charge towards the point of interest at point P. So therefore, if we are now asked how much is the electric potential due to this segment of charge or infinitesimal charge, then the answer is we are calculating also an infinitesimal electric potential. So therefore, this can be treated as point charge. So therefore, we have now the electric constant multiplied by the point charge. This is now dq. Take note that this dq is the part of q. So therefore, because this is already a very, very small, then we can say it point charge. So therefore, dq over r. Then integrating this one, okay, but take note, r is square root of x squared plus a squared because this is a right triangle, okay, and this is 90 degrees. While x is the distance from the center and a is our radius, so therefore r is equivalent to square root of x squared plus a squared. Okay, so integrating this one, because this is kind of differential equation, then we come up with the electric potential, which is equal to 1 over 4 pi permittivity, the integral of dq over r. So therefore, we need to substitute dq and r, and after that integrate, so that we can solve for the value of the electric potential at point P because of this ring charge. So therefore, dq, what is dq? R is nothing to worry because this is equivalent to x square root of x squared plus a squared. Now dq is take note, this is a segment. So therefore, if this is dq, then we have a very small length of the charge, call this as ds. And take note, for every segment of this ring, we have the so-called line charge density. No? Kindly review the definition of the linear charge density on our video on the electric field of a ring charge. Now take note again that linear charge density has a unit of coulomb per meter. So therefore, this is actually the charge per length of the conductor. So therefore, ds is the length. Then it follows that this this linear charge density, if given the q, this is just equal to dividing that by the length. So q as the entire charge divided by the length of the ring. The length of the ring is, take note, this is circumference of the circle. So the radius is a. So therefore the circumference is 2 pi a. So q divided by 2 pi a is our linear charge density. Okay? So therefore, at the same time, linear charge density in terms of dq is just the same as dq, okay? Because this is the charge of this infinitesimal segment divided by the length, which is ds. So therefore, linear charge density is dq over ds. So if we take diagonal product of this, then dq is the linear charge density multiplied by the infinitesimal length of the ring. Okay, remember again, we cannot use dq. Why? Because this is a ring charge. Okay, so therefore, that's why we use the linear charge density. But this linear charge density is actually in terms of our dq. So replacing dq here, dq is linear times d. So therefore, we can substitute it here also with r here. So therefore, take note that our limit is what? The limit is, if you run this one integration, the limit will start from 0, which means the starting point of our ring. Then moving the segment, rotating this to the entire circumference of the circle, then it will close to this total distance of 2 pi length. Meaning if you cut this one and stretch this, the length is 2 pi a. Okay, then substitute the values again. Take note, okay. This is dq is what? dq is linear charge density times this, substituting here. Then r is, take note, is square root of x squared plus x squared. So therefore, we substituted r here. This is r, okay? This is r. And this one is, take note that linear charge density is constant. So we can take it out including r because r will not change when this segment runs to all throughout the ring. R is always r. So therefore, r will not be affected if we integrate if we evaluate integral. So the only affected is the ds. So therefore, everything should be put outside the integral. So therefore, this will be the outside. But take note, what is linear charge density again? This is q over 2 pi a. So therefore, this is q over 2 pi a. While r outside is this one, the square root of x squared plus a squared. So therefore, what we have now inside integral is only the ds. So integrating, this is basic. So the integral over differential is the function. So we have this as is. The limit is from 0 to 2 pi a. Okay, so evaluating the integral, we come up with 2 pi a. Take note, q again, over 2 pi a is our lambda, while r square root of x squared plus a squared. And this is the electric constant. Okay, now look at this one. This will be cancelled out. This will be cancelled out. So therefore, we have what? 1 over 4 pi permittivity, the electric constant multiplied by q over the square root of x squared plus e squared. This is the electric potential of ring charged particle. Okay? Now remember that this electric potential is directed from the center. Take note, from the center of the from the center of the circle extended towards P. Okay? So therefore, X, to calculate the electric field at point P, you need only the constant, that charge, the entire charge, okay? Entire charge divided by the square root of x squared plus a squared. This is the potential at that point. Now question, what if you are asked to solve for the electric potential not in the center of this, from the center? The answer is, you cannot solve. This is not applicable. You have another formula in order to solve for that problem. So in this problem, this is only limited for the electric potential at that point, extending x towards the far away distance. Okay, so therefore, now let's apply. Take note. Remember that the electric potential of a ring, again, is 1 over 4 pi permittivity q over square root of x squared plus x squared. Okay, this is the where x, again, is coming from the center and a is the radius. Then r is the square root of x squared plus r squared. The problem says that a ring has a diameter. Okay, diameter is 8 centimeter. Now take note that a is radius. So all you need to do is to divide the diameter by 2 and the result is radius. Now, this is the charge is fixed at the place that carries the charge. So therefore, this is an stationary charge whose charge is positive microcoulomb. Okay, uniformly spread over its circumference. Therefore, the charge was spread throughout the length uniformly. Okay, then uh, the mass of that. Okay, okay, over the circumference. The letter A, you're asked how much work does it take to move the tiny, a small charge, which is 3 microcoulomb, charge ball, whose mass is 1.5 grams from a very far away distance to the center of the ring, which means that we will calculate the work done from a point far away from this charge, okay, towards the center of the circle. The center of the circle is located at 0 origin here. Okay, that's the problem in letter A. How much work done? So W, you are asked to solve for the work done. Letter B, is it necessary to take the path along the axis of the ring? Which means that do we need to use the path? Those are questions. Letter B, if the ball is slightly displaced from the center of the ring, therefore, if we have this charge here, and we will displace this charge, which is 3 microcoulombs away, slightly away from the center, what will be the resulting effect, or what will be the result after? Okay, then you are asked to solve for the maximum speed that will it will reach to that point. Okay, maximum speed. So where is the point where it produces a maximum? Okay, so we have to identify what point where the velocity of the charge be maximum. So therefore, this is the problem. Okay, you are asked 3 questions here with follow-up questions. So take note, this is a ring. So if this is a ring, then we can use this formula we derived before in our previous slide. Take note that at any point along this line, radially from the radius perpendicular, okay, from the center perpendicular to the radius, the electric potential is y over 4 pi permittivity q square root of x squared plus a squared. Okay, let's apply this formula. So take note that the problem is how much work does it take for a tiny charge ball from far away distance to the center of the ring. So therefore, okay, we have to locate points here. we will locate points. But take note that one point should be at the, this is the final point. The final point is located at x is equal to what? If the problem is from the center of the circle, so therefore x must be what? X must be 0. So therefore, if we say that the final point is located at the center, we must equate x be equal to 0. So you have to substitute it here. Okay? So what will happen to your R therefore? Your R now substituting x here 0 will becomes what? Will becomes, because this is 0 plus a squared x square root, the answer is just equal to a, which means that this line will coincide exactly at this line. And R now becomes a because this is 0. And this is where the point, where the final, where the charge arrive at this final point. This is the final point. And the initial point is far away distance. So therefore, okay, so there, this is now the result. This is our point. See it in point zero, okay? Then, this is our initial, or this is the final velocity. We call this as V naught. This is V naught. Then, in a far away distance, we have here point B, okay? Far away distance, which means that this is R, the radius or the distance from the center of the charge is infinite, okay? So if this is infinite, okay, so what will you do? Okay, all you need to do is take note, in a far away distance, this will become 0. Okay, this will become, look at the formula. If we substitute R be an infinite distance, so this will becomes infinite, the denominator is a very large number, so therefore this will becomes 0. It will happen only that electric potential be 0 if if that point is located in a far away distance, which means at infinite value of R. Okay, so we have now 2 points. What is the question again? How much work does it take for a tiny? So therefore, we have this charge moving from what? Moving from A towards the center of the circle. So this will be our starting point, and it will end up to this point. Okay, it will end up to this point. So take note that when you look at the situation, this is against the force. Why? Because it is positive. Take note, in positive charge, force is radially outward. So therefore, if you want to move the charge from point B towards point O, where located at the center of the circle, then you must exert a force on it. You have to exert a force because this is against the electrostatic force. You have to apply a force. So therefore, expected that the work done, the answer of this work done must be a negative. Negative means the force is an opposite to the displacement. Okay? So, okay, now how will we answer this problem? Work done. Okay. You review your notes on the previous video. When we say work done from A to B, okay? So, from A to B. This one is from B to O, okay? Work done from B to O is, take note, it is what? The negative change in potential energy. If you remember, again, in our previous definition of work done, the work done from A to B is the negative change in gravitational or electric potential energy. So therefore, again, okay, the work done from B to O is negative change in electric potential energy. So what do you mean by change in electric potential energy? Change means final minus initial. So in this case, we have two points. We have the initial, this is the initial, and this is our final, because the problem says from B to the center. So therefore, okay, substituting this one, this should be final. The final should be the energy at point O. Assign that as U naught. Okay. Then the initial is UB, means the energy at point B. So take note that this is minus. So therefore, okay. Now, if I divide both sides by the moving charge, okay, dividing both sides by the moving charge, what will happen is, this will becomes U naught over Q naught, and this is UB over QB. Now, what is U over Q? Recall the definition of electric potential. Electric potential is defined as the energy per charge. So therefore, if you divide this U naught by Q naught, it is the electric potential at point. Therefore, the answer should be V naught. While this one, UB over Q naught is the potential at point B. See it, VB. Okay? Now, take note that the potential at B is 0. So, therefore, we will substitute the 0. And take note, the U naught over Q naught is V naught, or the electric potential at the center of the circle. Okay. So, continue. This is 0, remember. Okay. So, therefore, if you cross multiply this one, because we want to solve, this is a question. Work done by what? Work done by the charge 3 microcoulomb moving from B to O. And the answer is, okay, the answer is, okay, now take note that what is potential? Okay, what is potential at the center? Look at the definition, okay, definition. The center, okay, electric potential is, using this formula, this is 1 over 4 pi permittivity, take note negative, and this is the charge of the entire charge of the ring divided by A. Why is it A? Okay, because take note that R at the center is equal to A, because this is where when x equal to 0, when you substitute here x be equal to 0, then square root of that, a squared is simply as a. So therefore, this one is taken from the formula. Okay, so we have now the value of the negative V naught, or the potential at the center, which is equal to negative 1 over 4 pi permittivity Q over A. Okay, so therefore, we will now we will consider this equation, this one, okay, this member and this member. So therefore, this is now the equation. Okay, so solving for again for the work done from B to O, take diagonal product. So we have the negative 1 over 4 pi permittivity Q naught, which is the moving charge, and this is the charge of the ring divided by A. Okay, again, look at the negative sign. So this is consistent in our explanation that in order to arrive the charge from far away distance towards the center, it needs a negative force. Okay, you have to counter, so you have to exert a force, and the work done should be negative. Okay, so therefore, take note that U naught is what? How much? U naught is 3 microcoulomb. Convert that into coulomb times 10 raised to negative 6, while Q is what? 5. And this is micro again, so times 10 raised to negative 6, because negative 6 is micro. Divided by A. What is your A? Okay? What is your A? Okay. Take note that the given problem is diameter. Now, 1/2 of diameter is radius. So, 8 centimeters divided by 2, our radius is 4 cm. Okay? So, this 4 cm will be substituted it here, then convert that into equivalent meter. Okay, let's do it. The constant is again 9 times 10 raised to 9. Negative is this negative sign. And this is the charge of the moving charge, 3 microcoulomb. And this is multiplied by 10 raised to negative 6. While this one is the charge of the ring, the 5 microcoulomb multiplied by 10 raised to negative 6 for the micro, then divided by the radius. Okay, our A is 4. Okay, our A is 4. then times 10 raised to negative 2 for the meter equivalent. So then simplify, use your calculator, we come up with negative 3.375 joules. Negative means the force is against the electric force. This means that you are moving against the electric. This like water flowing towards you and you want to move upstream. So therefore, you have to exert more effort. So in order to arrive at the center, you need the negative work done of 3.375 joules. This is the answer for letter A. Okay, letter B. Look at letter B. Okay. Is it necessary to take the path along the axis of the ring? We need to take always just to answer, okay, the work done. The answer is not necessary, okay. It is not necessary because take note that both work and the change in energy does not depend on path. Therefore, you can place anywhere. If you are talking about work done and change in, take note, change in energy, okay. So therefore, but the potential may differs, okay. It has a different potential, but the work done and the energy does not depend on the path. So therefore, the answer is no. Okay. Letter C. Letter C is if the ball is slightly displaced from the center. So imagine the ball now is on the ring because it was pushed through the ring. Now what will happen? Okay. What will happen if you move slightly from the center? So what will happen is, okay, take note that remember that the ball with charge of 3 microcoulomb was pushed by a force. Okay, you are exerting force on it. Now if you slightly detach that at a certain distance, then that ball will move away from that center surely. Okay. Okay. Now the question is, follow-up question, what will it do? Okay, so it moves in far away distance. It will go back to the point where the potential becomes zero. Okay, then what will be the maximum speed it will reach? So if you imagine, just like putting an object on a spring, compressed spring, then suddenly release. Okay, if you are asked what is the maximum, so it should be the velocity at that point. The velocity at that point is the maximum velocity. Okay, so therefore, okay, no, this is not. It will go back. We will correct this one. This it will. No, this is not the one. The correct answer is when you slightly place the object from the center. Okay, slightly place from the center of the ring, it will move. Okay, it will move from the center out of the ring. Okay, so it will move towards the infinite distance where the potential now becomes zero. Okay, let's proceed to the follow-up question. What is the maximum speed it will reach? Again, the maximum should be at the center. Okay, so therefore, take note that work done, the work energy theory means the work done from B to O is negative change in kinetic energy. This is work done energy theorem. Okay. Now, what is the meaning of change? It should be the final minus initial. Take note that the final is located at the center of the ring. So therefore, this should be K0. K0 means the final kinetic energy, where KB means the initial kinetic energy. This is the kinetic energy at the final, at the far away distance. So therefore, this must be zero. Okay. this must be 0 because in the final, it is at rest. So therefore, if it's at rest, velocity is 0 because kinetic energy is possessed by velocity. So therefore, this should be 0. So therefore, the work done from B to O is the kinetic energy. Okay? So therefore, okay. So substituting, what is K? What is the definition of K? This is 1 half mv squared. Okay? So therefore, multiplying by the mass of that charge, which is 1.5 grams, multiplied by the square of the velocity. Take note, this should be maximum. Okay? This is maximum. Now, take note that our work done is negative. Okay? So take the absolute of that. Why? Because we want to know how much the magnitude of the velocity. Take note, the velocity is against the, okay, this is towards the far away distant point. So therefore, it will produce a reverse, okay, reverse direction of that from the exerted energy, negative 3. So take the absolute of that. Okay, then solve for the final velocity. This is square root of 2. Work done from B to O divided by M. Then everything, take the square root of that. Okay, substitute the values. This is, take note, disregard the sign because this is absolute. And the mass is, the 1.5 grams divided by 1,000 is 0.0015 or times 10 raised to negative 3. Okay? In exponential form. So therefore, then the answer is 67.08 meter per second. This is the maximum speed that the ball can do. And it happens at what point? This happens at the center of the ball because it will be uh, repelled from the charge. Repelled, why? Because this is positive charge. This is positive charge and this is also a positive charge. Positive, the same polarity repel each other. So therefore, since our ring charge was held fixed, so therefore it was the tiny charge will move away from that charge, and it will be in opposite and in distance moving away from it. So therefore, the maximum should be at the center of the ring. Okay, so that's all for this problem. I hope you learned about how to calculate the electric potential of a ring. In our third video of this electric potential calculations, we will derive the relations of the electric potential of the infinite or the finite line charge. In video number 1, for the calculation of electric potential, we calculate the electric potential of what? The infinite line or the cylinder, conducting cylinder. Now, the third video will calculate the electric potential of finite finite line charge. Okay, see you on the next video.